Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss double integrals over general regions. And we will see, in fact, that any general region can be reduced to two simple types of regions. One is called type 1 and the other is called type 2. We will discuss this in this video. So let's go directly to the general theorem here. So we have the following theorem: let f of xy be continuous on a region R, and we'll consider two types of regions, two simple types of regions. The first one is called type 1 regions. And a type 1 region, the general shape of the region is given as follows here in this graph. This region, you can think of it as a region over an x interval, AB, between two curves, a lower and an upper curve. So it is a region between an upper and a lower curve over an x interval. We describe this region mathematically by the inset notation as follows. So the region here, it is the set of all points xy in the plane, such that the x values are between a and b, in the interval a and b. And to see this, you just take arbitrary points here, x, and take a vertical line through the region here, and this is the corresponding x and y between g1 and g2, y between g1 of x and g2 of x. So this point xy here, y corresponding to x, the value of x is always between a and b, this is the x interval, and y between the two curves, g1 and g2. So regions of type 1 are described in this manner, and it is good to think of them as really a region bounded between a lower and an upper curve. So the lower curve here is g1 and the upper curve is g2. The region is bounded below by g1, this is the lower curve. The region is bounded from above by g2, so we call it the upper curve. So this interval consists of all points xy, such that x between a and b, the x interval, and y between the lower and the upper curve. In this case, the double integral of xy dA over r. Here dA equals dx dy or dy dx, as we know. But here, if the region R is a type 1, we have to start integrating with respect to y. So here, double integral of xy, we have to start integrating with respect to y. Okay, then with respect to what are the limits of y? The limits of y for the inner, they come from the description g1 to g2. The lower to the upper. So this is g1, y equal g1 of x, and y equal g2 of x, from the lower to the upper curve. And the x interval will be from a to b. So this is how to set up the limits of integration in case the region R is of type 1. We have a second region, which is a type 2 region. We call it a type 2 region, and here it is really a region bounded between two curves still, but it is now right and left curve. And the interval is on the y-axis. The situation really is similar. So here, if I take arbitrary y, and then just take a horizontal line here, and this is x and y. This region can be described as follows in set notation. It consists of all points xy, such that the possible values of y are the y interval, C to D. C to D. And for any y, the possible values of x goes from this x to this x. This comes from the left curve, which is hy, and this comes from the right curve, which is h2. So x goes from h1 to h2. h1 of y less than or equals x less than h of 2y. So for each y between C and D, x goes from h1 to h2. And we say here it is the left curve and the right curve. So this region can be described by a region which is on the y interval bounded between two curves, a left curve which is hy and a right curve which is h2. And in set notation it is given in this manner. So in this case the double integral of f of xy dA over the region R. Here we have to start integrating with respect to x first. So here this is f of xy dx. Then with respect to y, the limits are with respect to x, so I take the x limits, h1, h2, the left curve, the right curve, from the left curve which is h1 to the right curve which is h2 of y. After we integrate, then integrate with respect to y, and the y limits are c to d. So this is how to set up the limits of integration in case the region R is of type 2. If you take a general region, we can always divide it into sub-regions, each either of type 1 or of type 2. And then you just apply the same thing in each sub-region. So this is how to set up the limits of integration in case the region is of type 1 or of type 2. Now let's give an illustrative example about double integrals over general regions. So evaluate the double integral of xy dA over R, where R is the region bounded by the curves y equals root x and y equals x squared. The first step in the evaluation is to set up the limits of integration. And for that we have to sketch the region R and decide whether it is of type 1 or of type 2. So let's start. Let me take this solution here. So the region here, we have the following. We have the region y. It is the region bounded by the curves y equals root x. So this is y equals root x. And y equals x squared. This is y equals x squared. And the region bounded between these two curves is this region. So this is the required region. This is the region R. This is the region R. So here, before we do anything, notice that really we have the two curves. The two curves intersect at 2 points. So we find the point of intersection. If you solve x squared equals root x, okay. If you solve this, so I will leave this for you, get 2 points of intersection, 0 and 1. So this is really 0 and this is 1. So we have this, these are the values for the point of intersection. Now what type of region is this one? Well, I can just take arbitrary x here, and take a vertical line. So, and I always enter through x squared and leave through root x. So this is really x squared, and this is x root x. For any x between 0 and 1, I enter through x squared and leave it through root x. It is a region bounded between two curves, So it is the lower and the upper. The lower curve, lower, and this is the upper. upper curve. So I can write this region as follows. R consists of all points xy such that x between 0 and 1 and y, take any point here, xy, y is between x squared and root x. X squared less than y less than root x. So this is the region R. So the region R consists of all points xy such that x between 0 and 1 and y between x squared and root x. So it is type 1. So it is a type 1 region. Lower and upper. The lower is x squared, the upper is the root x. Since it is a type 1, we have to start integrating with respect to y. So this is x plus y dA over the region R, and this equals double integral of x plus y, first with respect to y. The limits are x squared to root x, x squared to root x. The lower to the upper. The lower is x squared, the upper is root x. And then dx, and they are from 0 to 1. This is how we set up the limits of integration. Now you integrate the inner first. So this is 0 to 1. With respect to y, this is x, y plus half y squared. From y equals x squared to y equals root x dx. So I substitute in the place of y. Okay, so this becomes x root x. This is x root x plus half root x squared x minus x squared, x cubed, plus half x power 4 from 0 to 1 dx. We integrate this one, so this is now, this is an x power 3 over 2, so this is x power 3 over 2, so when you integrate with x power 5 over 2, 2 over 5, plus 1 over 4 x squared minus 1 over 4 x power 4 plus 1 over 10 x power 10 from 0 to 1 x power 5, sorry. Substitute, this is when x equals 1, 2 over 5 plus 1 over 4 minus 1 over 4 plus 1 over 10 minus 0, and this equals just 10. This will cancel out. 4 plus 1, 5, 10, 2, 4 plus 1, 5. And this is just half. This is half. So this is the answer. Let's consider the following problem. Evaluate the double integral of x dA over r, where r is the region bounded by the curves x equals y squared and x equals 1. So to evaluate, first we have to set up the limits of integration, and to set up the limits of integration we have to decide whether the region is of type 1 or of type 2. And for that we have to sketch first the region. So let's sketch the region here. So this is the region x and y. We have the region bounded by the curves x equals y squared. So this is the horizontal parabola. So this is x equals y squared, and the line x equals 1. So this is the line x equals 1. A vertical line. This is 1, and this is x equals 1. So the region is the following region. This is the region. Okay. It is bounded between a vertical line and a parabola, horizontal parabola. And we notice here that really there are 2 points of intersection, so it is better to find these. So points of intersection. Here we set the two equations together. So x equals y squared and x equals 1. Just equate x with x. So we get y squared equals 1. And here we have just two values, plus or minus 1. So this point here, 1, y equals 1. And this point is minus 1. And it is obvious that really it is a type 2 region, type 2 region. In fact, you have a left curve, which is the parabola, and a right curve, which is the line. If it is not clear, you take arbitrary point y on the y-axis, and then take a horizontal line. This is y, this is the corresponding x and y. And you will notice that really y is always between -1 and 1, and x between these two x's. This is x equals y squared. This is x squared y squared x. And here this is just x, which is 1, and this is y. Okay, this is y. So if I take any point y here, notice, take this line and just move it around. Always the left curve will be the parabola and the right curve will be the line. Okay. So it is a type 2 region, and so we write it in this manner. R, describe it here, x between the left curve and the right curve. The left curve is always y squared, the parabola. X equals y squared, and the right curve is the line x equals 1, so this is x equals 1. And y is always between -1 and 1, so this is -1 less than or equals y less than 1. So this is a type 2 region. So to evaluate, I have to integrate with respect to x first. So we get the following: double integral of x dA over r equal double integral of x, first dx and then dy. What are the limits of x? The right curve to the left curve, y squared to x equals 1, and the limits of y are -1 to 1. So this is the limits of integration for this double integral. Now we evaluate the usual manner. We have to start with the inner integral. So this is -1 to 1. The integral with respect to x, this is half x squared from x equals y squared to x equals 1, then dy. Substitute x, this gives us the following: -1 to 1, this is half minus half y power 4 dy. Now integrate with respect to y, so this is half y minus 1 over 10 y power 5 from -1 to 1, and substitute. When y equals 1, I get 1 over 2 minus 1 over 10 minus, when y equals -1, I get minus half plus 1 over 10. Simplify, this is just half minus 1 over 10 plus half minus 1 over 10, and this is 1 minus 2 over 10, which is 1 minus 1 over 5, and hence this is 5, which is 4 over 5. So this is the value of the integral. Let's consider the following problem. Sketch the region of integration and write an equivalent double integral with the order dx dy. So here we have a double integral of a function, general function, with dy dx. The objective is to write the same or an equivalent double integral, but with the order dx dy instead of dy dx. i.e., this is a double integral written of type 1 dy dx. This is the setup when r is of type 1. We need to write it in the order dx dy as a type 2. Okay. So this is the objective of this problem. Basically, implicitly, this says in fact many regions are both type 1 and type 2. Many regions are both type 1 and type 2. So in that case, we can write the double integral as a type 1 dy dx or as a type 2 dx dy. So here the double integral is given as a type 1. We need to write it as a type 2. This is the objective. For that, we have to sketch the region. So what is the region given in this integral? Sketch it and let's see how to reverse the order of integration. So the region here R. Okay. We can read it from the limits of integration. So here x between 1 and 2. So the limits of x are between 1 and 2. So this is x between 1 and 2. And y between 0 and ln x. So y between 0 and ln x. So these are the limits. Okay. So y between 0 and ln x and x between 1 and 2. Now I can sketch this region as follows. This is the following here. This is x and this is y. Y, the lower curve is 0, y equal to 0. So it is just the x-axis. So this is y equal 0. This is y equal 0. And the upper curve is y equals ln x. So this is y equals ln x. So this is 1. Y equals ln x. This is 1. So the lower curve is the x-axis and the upper curve is the ln, the logarithmic function. And x between 1 and 2. So this is 1 and this is 2. This is 2. This is x equals 2 and this is x equals 1. So just above. So this is the region. According to this description, it is a type 1. It is a region over the x interval between a lower and upper. So this is type 1. Well, I have to describe this region as a type 2. To reverse the x dy, I have to describe it as a type 2. So here I will take the same region here. Okay. And this is 1 and this is 2 and this is x equals 2 and this is y equal to 0. And this is y equals ln x. And this is the region here. This is the same region. But I have to describe it as a type 2. As a type 2, I have to have a left curve and a right curve. And left curve and right curves are given as functions of y. So x equals a function of y. So here, y equals ln x. This gives me, I can solve it in terms of x. This gives x equals e power y. So this is the left curve. It is x e power y. And the right curve is just the line. X equals. And what is the y interval here? Just find the point of intersection here. The y interval from y equals 0, so this is 0, the x-axis, to y equals, well, if x equals 2 and y equals ln x, then y equals ln 2. So this is the corresponding y. For the left curve is the e power y, and the right curve is x equals to. Or take arbitrary y here. Take a horizontal line. So this is arbitrary x and y. This point, you always go through the region, through this point, which is y. And what is x? E power y. E power y. And you leave it through this point, which is 2 and y. 2 and y. You always go through e power y, the right curve. And you always leave x equals to the left curve. So here this r, in this case, r can be described as follows. X between the left curve and the right curve. The left curve is e power y. E power y. And the right curve is x equals to. And y between 0 to ln to 0 and ln 2. So this is how we describe the same region, but as a type 2. In this case, so now the given integral 1 to 2, 0 to ln x of xy dy dx equal. This is type 1. You write it as type 2. Type 2 of xy dx dy. The limits of x, e power y to 2. E power y to 2. And the limits of y are from 0 to ln 0 to ln 2. And this is how to reverse the order of integration from dy dx to dx dy, or describing really the same region as type 1 and as type 2. Lower, upper, left, right, left, right. So this is the answer. Now we consider the following problem. Evaluate the double integral 0 to 1 root y to 1 of sine by x cubed dx dy. Well, it is natural to start just integrating the inner then the outer. But if you look at the inner here, integrating sine by x cubed with respect to x. Here, the integration is not easy, or you can say it is impossible. Okay? In fact, we don't know how to integrate sine by x cubed dx. There is no simple function whose derivative is sine by x cubed. But we didn't know how to integrate this function. And in fact, there are many similar functions. For example, e power x squared, or e power x cubed, or e power x power 3 sine x squared, or any higher power cosine x squared, or any higher power. All of these are examples that are not easy to integrate, and in fact we don't know how to integrate these. We cannot find a simple function or an elementary function or a familiar function whose derivative is any one of these. So really here, if I want to evaluate, well, I cannot evaluate the inner integral. We cannot integrate the inner integral. So in that case, what do we do? What do we do if we cannot integrate? Here, the idea is just really to try to switch the order of integration. Write an equivalent double integral with the order dy dx instead of dx dy. So try to reverse the order of integration. So this is what we should do now. So we cannot integrate, then reverse the order of integration. Reverse the order of integration. Order of integration. So it is dx dy. You have to write it, change it to reverse to dy dx. Dy dx. in an equivalent way. If the double integral is given as dx dy, this is ايش then a type 2 integral. I have to write it as dy dx as a type 1 integral, as a type 1 integral. So going from type 2 to type 1. So how to do that? Well, we just sketch the region. What is R? This is the region R here. The limits of y are 0 to the limits of x. This is from root y, less than x, less than 1. These are the limits of y. Then the limits of y 0 to 1. 0 less than y less than 1. So this is the description of the region. Sketch this region here. So this is the region. X equals root y. This is here. X equals root y, which is just y equals x squared. Y equals x squared. So this is the region here. So this is x equals root y, x root y. To x equals 1, x equals 1. So this is x equals 1. And y between 0 and 1. So this is 0. And if x equals 1, y equals 1 also. So this is 1. So this is 1. So the region is what now? This is a type 2. Type 2. So we have really two pieces. Is my region the one above or the one below? Notice here the right curve is root y. So I enter the region through root y and leave it through 1. So this is really my region. This is my region here. This is the region. If I take a horizontal line at any y, I enter through here, which is root y, and I leave it through here, which is x equals 1. So really this is my region. Okay, and y between 0 and 1. Okay. So this is a type 2 region. Now describe this region as a type 1. So I take the same region here, So this is the same region. So this is 1, and this is 0, and this is also 1. And the curve x equals root y, it is just y equals x squared. Y equals x squared. And this is the region, the same region. But now we look at it as a type 1. So lower and upper curve, lower and upper curve. So this is type 1. So here if I take any x here, take a vertical line, well, the lower, clearly it is the y-axis, so this is x0, and this is x squared. So the lower is the x-axis, and the upper is the parabola. So here I describe R in this manner here. X between 0 and 1, the x interval, 0 to 1, but the y, the lower is the x-axis, y equal to 0, and the upper is the x squared, the parabola x. So this is the description of the region R as a type 1. Now, so my original integral, 0 to 1, root y to 1, sine by x cubed, dx dy. Now this is equals to double integral, the same function, sine by x cubed. When you reverse dy dx. Now the inner is with respect to y, so what are the limits of y? 0 to x squared, 0 to x squared, and the limits of x are 0 to 1. So really, when you reverse the order of integration dx dy to dy dx, the limits of integration will change. The limits of integration will change. They are not the same. This is very, very important. Now we integrate. Now this is now very simple to integrate. When you integrate a function of x only with respect to y, so this is really a constant with respect to y. So when you integrate, this is just sine by x cubed times y from y equals 0 to y equals x squared. And this is the outer 0 to 1, and this is the outer d dx. Integration becomes very simple when you reverse the order of integration. This equals 0 to 1. This is sine by x cubed. This is x squared minus 0 d dx, which is just x squared. This is just x squared. So this is just x squared. X squared. Well, how to integrate this one? This is just a simple u substitution. Let u equals by x cubed. The derivative is x squared times 3 by. Okay. A simple u substitution gives us the following. This is minus cosine by x cubed over 3 by over 3 by from 0 to 1, from 0 to 1, and this becomes cosine by, this is minus cosine by over 3 by, this is minus 1 over 3 by, minus cosine 0, 1 over 3 by, 1 over 3 by, and the answer will be 2 over 3 by, 2 over 3 by. So this is the answer. So the idea here again, just reverse the order of integration, write the integral from type 2 to type 1, or in other problems from type 1 to type 2. Then integration becomes very, very, very simple. Let's consider the following problem. Find the volume of the solid under the paraboloid z equals x squared plus y squared and above the triangular region with vertices 0, 0, 0, 1 and 1 and 1. So it is an application problem. It is a volume problem. So it is better to just visualize the solid. So let's just try to sketch the solid here. So we have the 3 space here. This is x and y, and this is z, and we have the paraboloid z equals x squared plus y squared. So this is the general graph of the paraboloid. So this is the paraboloid z equals x squared plus y squared. This is a paraboloid. This is the surface. Okay, so under the paraboloid and above the triangular region with the vertices 0, 0, 0, 1 and 1 and 1. So it is now in the xy plane. In the xy plane I have 0, 0. So this is 0, 0 and 0 and 1. So this is 0 and 1 and 1 and 1. So this is 1 and 1 here. So this is the region here. This is the region. This is the region in the x. So I have a paraboloid, and then I have a region in the first octant, or in the first quadrant of the xy plane. And I need the solid below and above the triangular region. It is better in this case, just to take the region here in the xy plane and just draw it. This is R, so this is just draw it in the xy plane, just to make the region clear. So here, this is the region R in the xy plane. So this is x and this is y. And I have the vertices 0, 0 and 0 and 1. So this is 0 and 1. And this is 1 and 1. This is 1 and 1. So this is the triangular region. So this is my triangular region in the XY plane. Okay. If I have the paraboloid and I have this triangular region, so my solid will be just in the first octant. Well, how to find the volume? Well, by the formula. Well, the function is positive and over a region, so it is just the double integral. This is the main application of double integral. So the volume will be given as follows. The volume will be double integral of the function, the surface, x squared plus y squared dA over the region R. So this is the formula. It is double integral of the function. The function is positive and continuous over a region R. So this is the formula to compute the volume. Now here we have the next step to evaluate. I have to set up the limits of integration. Well, so it depends on the region. So is the region of type 1 or of type 2? Well, you can think of it as clearly, in fact, it is both type 1 and type 2. So if you consider it as lower and upper, this is the lower curve, this is the line, and the horizontal line is the upper curve. If you want it as left and right, the left curve will be the y-axis, and the right curve will be the line also. So it is really both type 1 and type 2. So I will just write, I will choose it, I will look at it as a type 1. Here I will look at it as a type 1. So this is 1. What is the equation of the lower curve? Well, this is a line from 0, 0 to 1, 1. Well, it is very simple to find the equation of a line passing through 2 points. You can find the slope, and 1 point you can find it, and it is very simple. And the equation here, y equals x. For the horizontal line here, this is h, y equals 1. It passes through this point, so it is y equals 1. So the lower curve is y equals x. The upper curve is y equals 1. So this is x here. If I go vertically, okay, this is the lower root x, and this is the upper, y equals 1. So here are x between 0 and 1, and y between the lower curve, which is y equals x, and the upper curve, which is y equals 1. So it is a type 1 region, type 1 region. So now I set up the limits of integration. So first dy, so this is x squared plus y squared. First dy, then dx. The limits of y from x to 1, this is from x to 1, and the limits of x are from 0 to 1. We integrate now, this is 0 to 1, the inner integral. You integrate with respect to y, so this is x squared, y plus 1/3 y cubed, from y equals x to y equals 1 dx. And this is 0 to 1. When y equals 1, you get x squared plus 1/3 minus, when y equals x, you get x cubed plus 1/3 x cubed dx. And this is just 0 to 1. This is x squared plus 1/3 minus 4 over 3 x cubed dx. We integrate, and this becomes 1/3 x cubed plus 1/3 x minus 1 over 3 x power 4, from 0 to 1. Substitute 1, and 0, you get 1/3 plus 1/3 minus 1/3. The answer is just 1 over 3. So this is how to solve this volume problem. Let's consider the following problem. Find the volume of the solid in the first octant, bounded by the coordinate planes and the plane x plus y plus z equals 2. So it is a volume problem, so it is better to really set up the formula for the volume. It is better to sketch the solid itself. But let's try to sketch the solid. So this is the xy plane, the space, 3 space, x, y, and z. Find the volume of the solid in the first octant, so it is in the octant nearest to us or closest to us, bounded by the coordinate planes. So I have 3 planes, the xy plane, xz, and yz plane. By the coordinate planes. These are the coordinate planes in the first octant. xy plane, xz plane, and yz plane. And the plane x plus y plus z equals 2. So what is this plane? What is the graph of this plane? Well, to sketch the graph of this plane, the simplest way to sketch such a graph, the graph of any plane, is just to find the intercept. So what is the x-intercept, the y-intercept, and the z-intercept? For the x-intercept, I have to set y and z equals 0. 0, 0, I get h 2. So this is 2 here on the x-axis. The z-intercept, I set x and y 0. I put 0, 0, I get y, z equals 2. So this is also 2. And if for the y-intercept, if I set x equal to 0 and z equal to 0, I get y equals 2. So this is 2, this is 2. So these are 3 points on the plane, and the 3 points really are enough to determine a plane. So just join them. So this is the So the plane will extend, of course, but the part of the plane in the first octant will be just this triangular part, So this triangular part in the first octant is the part of the whole plane, My concern is just in the first octant. So the graph of the plane in the first octant is just this triangular plate, So now what is the solid? What is my solid? Well, it is the plane, it is the solid bounded by the 3 walls, floor and the 2 walls, the coordinate planes, and the plane x plus y plus z equals 2. So this is x plus y plus z equals 2. So the solid is everything below the plane and above this triangular region. So everything below this triangular plane. So this is H, the solid. This is the solid. So it is just like a solid in the corner of the room, bounded above by the plane, by this triangular plane. So now what is the formula for the volume? I have a solid, a surface, which is now the surface is the plane, and I have a region. What is the region? It is just the triangular region in the xy plane. So it is a solid below the plane and above this region, So this is really this region. So let me this is R in the xy plane, This is triangular region in the xy plane. So here the equation I can solve for z, because z equals 2 minus x minus y. It is the solid below this equation, a positive function, above the triangular region in the xy plane. A surface and a region. Then the volume, the formula for the volume, it is double integral of the function, which is 2 minus x minus y, 2 minus x minus y, dA, over the region, This is the formula. A surface above a region. The surface is positive and continuous. So this is the formula for the volume. Now I have to set up the limits of integration. So describe R. So just it is better just to bring R to the XY plane just to make the picture clearer for us. So this is X and this is Y. And here in the X-axis it is 2 and in the Y-axis it is 2 also. So this is 2 and this is 2 here. And this is the line here. This is the line. Okay. And this is the region. This is the region R. This is R. This is R. R. Well, so this is the R. It is bounded between the X-axis and the Y-axis and this line. This line, you can find it in two ways. You have 2 points. You can find the equation of the line. Or, really, this line is exactly the same as this line. And this line comes from the plane. It is the intersection of the plane with the XY plane. With the XY plane. The equation of the XY plane is Z equal to 0. So when I set Z equal to 0 in the equation, I will get the equation of this line. So this is here, Z equal to 0 implies X plus Y plus 0 equals 2, and hence X plus Y equals 2. So this is the equation of this line. So really this equation, the equation of this line is X plus Y equals 2. Now this region, is it type 1 or type 2? In fact, it is both. So I will just look at it as a type 1. So here as a type 1, if I take X here, okay, the lower is the X-axis and the upper is this line, which is H, Y equals 2 minus X. So type 1, X between 0 and 2, and Y between the lower is the X-axis, Y equal to 0, and the upper is the line 2 minus X. This is the limit or the description of this region as a type 1. So now the limit will be the following: integral 2 minus X minus Y dy dx as a type 1. The limits of Y 0 to 2 minus X, 0 to 2 minus X, and the limits of X are from 0 to 2. So this is the setup of the double integral for the volume. The calculation is very simple and we leave it for you to try. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss some properties of double integrals, and we will see that really they are really similar to the properties of single integrals or integrals of 4 functions of one variable. For that, let's see the following theorem here. So let f of xy and g of xy be continuous functions on a closed and bounded region R. So we have a closed and bounded region R in the xy plane. The first property is the following: the double integral of a constant times a function equals, well, we can pull the constant outside to get constant times the double integral of xy. So basically you can pull a constant outside the integral. The second property is the double integral of R of a sum or difference of 2 functions, f plus minus g. We can separate, so it is the double integral of the first function f plus or minus the double integral of the second function g. Okay. In fact, the 2 properties follow from by using the definition. It is a limit of a double sum. So using the properties of the double sum and the properties of the limit, we get these 2 properties. The third property, if the region R is a union of 2 non-overlapping regions, R1 and R2. So we have a region R. It is the union of 2 regions, R1 and R2. The 2 regions are non-overlapping, or only they meet just at a boundary, at boundary points only. So if R is a union of 2 non-overlapping regions, R1 and R2, in this manner, then to find the double integral of f over the region R over the whole region, we can really split the integral into integrals over each region separately. So it is the double integral of f over R equal double integral of f over the first region R1 plus double integral of f over the second region R2. The property here is really similar to the property when we can divide an interval into two sub-intervals, non-disjoint or non-overlapping sub-intervals for functions of one variable. So this is the third property. Now with the fourth property, we have a specific one here. So when the function is 1, so what is the double integral of 1 over R? When the function is 1, here we will get really the value of this integral will be the area of the region R. The area of the region R. Let's see how we get this formula here, or this property. Of course, our function here, is just 1 of xy equals 1, or just z equals 1. Z equals 1. So this is the function. So we can think of this geometrically as follows. So you have the plane z equals 1 and the region R. So this is the region R here, R, and the plane z equals 1. So you have something like this really. So this is z equals 1. So we have z equals 1, plane z equals 1, this is the graph, and it is above this region. So geometrically, double integral of 1 over the region R, it will be the volume of this solid. So this is the real double integral of 1 over R dA equal just the volume of this cylinder, the volume of this cylinder, the volume of this solid. Of course, z equals 1. This is a plane z equals 1. Z equals 1. So it is the volume below the plane and above R. Okay. So geometrically, it is equal to the volume. But now here it is also a cylinder. We can find the volume by finding the area of the base times the height. Area of the base, which is R, area of R, times the height, the height of the cylinder. But the height of the cylinder is 1. From here to here, this is just 1. This is the height of the cylinder. And this becomes area of R times 1, and hence this is area of R. So when we evaluate the double integral of the function 1 over a region R, we get the area of R. In in calculus 2, the analogous property is the following. We have a function of x dx from 1 from a to b. When you integrate, you get b minus a. Geometrically, it is the length of the interval. AB. So single integral gives you the length of the integral, but double integral of 1 over a region, it will give us the area of the region R. So this is the fourth property. We consider next some properties about inequalities or inequality properties of double integral. So we have the fifth one. If f of xy is greater than or equal to 0 on R, so geometrically the graph of f is above the xy plane, then the double integral of f over R greater than or equal to 0. We can see this geometrically because if f is positive on a region R, then the geometric meaning of the double integral is a volume. So it is the volume below the graph of f and above R. And the volume has to be greater than or equal to 0. So if f is positive, then the volume has also to be greater than or equal to 0 or positive. The next one, if f of xy greater than or equal g of xy on the region R. Geometrically, it means the graph of f is above the graph of g. This is the meaning, the geometric meaning of the inequality. If the graph of f is above the graph of g, then the double integral of f over R greater than or equal double integral of g over R. We can also see this geometrically. If we assume that both of them are positive, then this is a volume and this is a volume. In that case, if the graph of f is above the graph of g, then the volume of the solid below f is larger than the volume of the solid below g. So the volume below f greater than the volume below g. So this is the sixth one. It is also nice to look at this inequality or this property in a different way. It is better or it is nice to look at it in this manner. Okay? If f is greater than or equals g on a region R, then we can integrate both sides without changing the inequality sign. So if f is greater than or equals g, then double integral of f over R greater than double integral of g over R. Integrate both sides without changing the inequality sign. The last one here, if the function of xy lies between two numbers m, small m and capital M. So small m and capital M are constants or just real numbers. If f lies between them on the region R, so the graph of f lies between two numbers on the region R, then we have this inequality, m times the area of R less than double integral of f less than capital M area of R. In fact, we can show this by combining property 6 and property 4. Well, with the two inequalities here, I can use this by double integral of each side. Double integral less than equal double integral less than equal double integral. So using this property twice. Now double integral of f is this one. What is double integral of little m over R? M is a constant, I can take it 1. Then double integral of 1 is just the area of R. So m times area of R. The same thing here, double integral of capital M. Capital M is constant, take it outside, get m, double integral of 1, which is also area of R. So if the function lies between two constants, two real numbers, then the double integral lies between m times the area of R and capital M times the area of R. Okay. The last property, it is about the calculation of the average value of a function. So the average value of a function of two variables of xy on the region R, which is still closed and bounded, is given by this formula. F average equals 1 over area of R times the double integral of f over R. So this is the formula to compute the average value of a function of two variables. Well, here this is really similar to or a generalization of the formula for functions of one variable. So if you have f of x for interval ab, the average value, if it is continuous here, the average value, it was 1 over b minus a, integral of f of x dx over ab. Here b minus a, it is just the length of the interval ab, ab. So for functions of two variables, we replace the length by the area of the region, R. So really it is a generalization of the formula for functions of one variable. So this is the formula for computing the average value of a function of two variables on a closed and bounded region R. Let's consider the following problem. Evaluate the double integral of xy plus 1 over R, where R is the region in the first quadrant enclosed by the curves y equals x, y equals 2x, and y equals 1 over x. So first we have to sketch the region R, because the main thing is just to set up the limits of integration. So we sketch the region R and decide whether it is a type 1 or a type 2 or something else. So this is the region R, this is the region, so this is the xy plane, x and y. I have y equals x, so this is y equals x, and y equals 2x, so this is y equals 2x. This is the second line, and the curve y equals 1 over x, so this is the curve y equals 1 over x. So this is y equals 1 over x. Now the region enclosed by these three curves is this region. So here, this is my region. This is the region. Now we ask, what kind of a region is this one? Is it a type 1 or a type 2? Well, here in fact, it is neither of type 1 nor of type 2. But we can split it. We can split it into two subregions to make them each of either type 1 or each of type 2. So here I can just split the region into two subregions. So this is the following. So here, when you make the split here, so I have a first region, so this is R1, which is now of type 1. So this is the lower and this is the upper curve. And the second region, R2. And it is also of type 1. This is the lower and this is the upper. And now when you split the region, you can split the region into two subregions, each of type 1. And for that, of course, we need to know what is the point of intersection. Okay, so here, between the curve y equals x and the curve y equals 1 over x, the point of intersection here is 1 over x equals x implies x squared equals 1, and hence x equals plus or minus 1. But in the first quadrant, we just take x equals 1. So this is 1. This is 1. Also, we have another point of intersection between the curve y 1 over x and y equals 2x. So here the second one, 1 over x and the line 2x. 1 over x and the line y equals 2. So this is x squared. X squared equals half. And this is x equals plus or minus 1 over root 2. But in the first quadrant, it is just 1 over root 2. 1 over root 2. 1 over root 2. So these are the two subregions. Now R1, I can describe it using inequality. It is x between 0 and 1 over root 2. From 0 to 1 over root 2. And y, here the lower curve is x, y equals x, and the upper curve is 2x. So in R1, y between x and 2x. The lower curve is y equals x, the upper curve is y equals 2x. For R2, x is between 1 over root 2 and 1. R2, x between 1 over root 2 to 1, and y. The lower curve is x, again y equals x, and the upper curve is 1 over x. So this one just 1 over x. 1 over x. So this is the description of the region R1, of the regions R1 and R2. So now if you want to find the double integral over R over the whole R, so double integral over the R xy plus 1 dA. Now R is a union of two non-overlapping regions, R1 and R2. R is a union of these two regions, so we just split the region R. So this becomes a double integral over R1, double integral over R1 of xy plus 1 dA plus double integral over R2 of xy plus 1 dA. Splitting the region R into two sub-regions, two non-overlapping sub-regions, R1 and R2. Now, based on the description of R1 and R2, we can set up the limits of integration. So this is xy plus 1. Now, as type 1, type 2, both of them are type 1. So R1 is of type 1, R2 is of type 2. Then we have to integrate first with respect to y and then with respect to x. So the inner with respect to y, so you put the limits of y, x to 2x, x to 2x, and then the outer with respect to x, 0 to 1 over root 2, 0, 1 over root. This is for R1. For R2, the same thing here again. R2 is a region of type 1. So we integrate first with respect to y, then with respect to x. The limits of y in the inner integral, x to 1 over x, so this is x to 1 over x, and the limits of x are 1 over root 2 to 1. 1 over root 2 to 1. So this is how we set up the limits of integration for the two regions. Now the next step is just we compute, and the computation is really not difficult, so just a direct computation. So we leave it for you to continue the solution. So we continue just direct calculation. We consider the following problem. Use a double integral to find the area of the region bounded by the curves y equals x squared and y equals x plus 2. So it is a region between two curves and we need to find the area. Of course, we can use the techniques of Math 102, Calculus 2, but here the question is to really use double integral, a suitable double integral to find the area of this region. And for the area using double integral, we have the following, really area of R, we have the following formula, area of R equals double integral of the function 1 dA over R. So this is one of the main properties of double integral. When you compute the double integral of the function 1, you get the area of the region R. The area of the region R. So if you want to compute area using the double integral, we have to use this formula. Now we have to set up the limits of integration, and this is based on the region R. So we go and sketch the region R. This is the region R here. You have y equals x squared, so this is the parabola, y equals x squared. And we have the line y equals x plus 2, so if x equal to 0, it is 2. And if x equals, let's say, if x equals so minus 1, for example, this becomes 1, so this is the This is the so if x equal to 0 it is 1, if x equals 2 it is 4. So this is the region, this is the region here, this is the region bounded between the two curves. So this is y equals x plus 2. As always we have 2 points of intersection, so it is better just to go and compute the 2 points of intersection. So the points of intersection, so you have x squared equals x plus 2, and this is just x squared minus x minus 2 equal to 0. When you factor, you get x minus 2 times x plus 1 equal to 0. And this gives us either x equals 2 or x equals minus 1. So here this point is minus 1, and here this point is 2. So these are the points of intersection. Now to set up the limits of integration, what type of a region is this one? Well, it is really, notice here this is the lower and this is the upper. Okay? So if you take any x here, well, I always enter the region through the lower, the parabola, and leave it through the line. Okay? So it is really a type 1 region, type 1 region. So R, the x interval will be minus 1 to 2, minus 1 less than x less than 2, and y between the lower curve and the upper curve. I enter through x squared, so this is the parabola, x squared is the lower, and the upper is the line, x plus 2. So at each x, always x squared less than x plus 2, x squared less than x plus 2. So this is the description of this region. Now I just go and compute. So this is area of R, double integral of 1 dA over R, and this is double integral of 1 type 1. So I have to start with integrating with respect to y first, dy, and then dx. And the limits of y, x squared to x plus 2. So this is x squared, and this is x plus 2. And the limits of x are minus 1 to 2, minus 1 to 2. Now we integrate first the inner, then the outer. When you integrate 1 with respect to y, I get y from y equals x squared to y equals x plus 2. And this is minus 1 to 2 dx. And this becomes minus 1 to 2. هتكون x plus 2 minus x squared dx. When you substitute. Now we integrate with respect to x. This is just half x squared plus 2x minus 1/3 x cubed from minus 1 to 2. Substitute 4 over 2, 2 plus 4 minus 8 over 3 minus half minus 2 plus 1/3. And this is just 6 minus 8 over 3 minus, this is minus 3 over 2 plus 1/3 plus 1/3. Okay, so this is again 6 plus 3 over 2, 6 plus 3 over 2 minus 8 over 3 minus 1 over 3 minus 9 over 3. This is 3 plus 6, this is 9, 9 plus 3 over 2, and this is just 2, 18 plus 3, 21. So this is the value of the area of the region Let's consider the following problem. Find the average value of xy equals xy over the triangular region with vertices 0, 0, 2, 0, and 2, and 2. So it is a problem about average value, so we just apply the formula. So this is of average. F average equals 1 over area of R, double integral of the function of xy over R dA. And the function is given as just x times y. So this is the formula, so we have just to apply the formula. So first, what is the region R? R is the region, it is the triangular region with vertices 0, 0, 2, 0, and 2, 2. So let's just sketch the region R. So this is R. I have the point 0, 0, and 2, 0, 1, and 2, and 2, and 2, 1, and 2. So this is the point. So this is these, and just join these points. So we have this region. So this is 2, and this is the region R. This is R. Well, just you can describe it. Of course, it is. It is very simple to find the line, the equation of this line, passing through 0, 0, and 2, 2. So it is just y equals x. And this line just x equals 2. And the base is just y equal to 0. Y equals 0. So this region R is a type 1 region. In fact, the lower is the x-axis and the upper is the y equals x. So it is type 1. Type 1 region. So we can describe it in this manner here. Okay. X, if I take any x here, well, I enter through the x-axis, y, and leave it through y equals x. The limits of x, the possible values of x are 0 to 2, 0 and 2. And y, the lower curve is the x-axis, y equal to 0, and the upper curve is y equals x. The line y equals x. So this is the description of the region R as a type 1 region. Now here to apply, so this is for the limits. Now we need also to find the area of R to apply the formula. So this is a triangle. What is the area of R? Area of R. It is a triangle, so it is half the base times the height. So this is half. The base of the triangle is this part from 0 to 2, so it is the base is 2. The base is 2. The height of the triangle is this distance, which is h, again 2, from 0 to 2. So this is the area equals to. The area of the region R is. Now substitute here, this becomes F average. F average equals 1 over the area of R is 2. Double integral. The function is x, y. Now for the limits, it is a type 1, so I have to start with dy first, then dx. For the inner integral, I need to find the limits of y, and the limits of y are from 0 to x, 0 to x. For the outer, I need the limits of x, and the limits of x are 0 to 2. 0 to 2. Next, we integrate. So integrate, so this is half. The outer 0 to 2, we leave it. For the inner, you integrate with respect to y, so this is x is a constant, and half y squared from y equals 0 to y equals x dx. This is for the inner. Substitute, so this is half integral 0 to 2. When you substitute x, half x squared minus 0 dx. And this is just half 0 to 2. This is half x cubed dx. We integrate one more time, so just take the half outside. So this is 1 over 4. Integral of x cubed, 1 over 4 x power 4 from 0 to 2. And this is 1 over 4 times 2 power 4, 16 over 4. This is 4 minus 0, and the answer is 1. So the average value of the given function over the triangular region are equals 1. The average value is 1.